Thanks, Alessandra. Okay, so what is the, so our main problem for this talk is the following. So it's a problem about bivariate forms or univariate polynomials. So you might think that there are no open problems left for univariate polynomials, but in fact that's not the case. So given, so it's called Waring problem or symmetric tensor decomposition. But in this talk, we're just going to focus mostly on bivariate things, although many things that I will say are going to be general. And I will try to point that out. So the problem, I give you a form in two variables of degree d. And I want to write f as a sum or linear combination of powers of linear forms in a minimal way. So I want to write this in a minimal way. So minimal with respect to r. Smallest r. And these LIs are linear forms. And the R, the minimal R, is referred to as Waring rank or symmetric tensor rank of F. Okay, so let me give you another completely equivalent problem, maybe a little bit more specific or a little bit more hands-on. This one might feel a little bit, well, if you haven't thought about it, a little bit strange. So equivalent problem. So this is equivalent when degree is even. So when degree is even, I can equivalently ask the following: given a Hankel matrix H. So what is a Hankel matrix? So H looks like this. And yes, let me fix sizes. K plus 1 by K plus 1. This K refers to the 2D. So the Hankel matrix looks like this. It is constant on anti-diagonal. CD minus 1, CD minus 1, CD minus 2. CD minus 2, CD minus 2, and then we go all the way down to C0. So equivalent problem is, so I'm giving you a Hankel matrix. Now, of course, if I want to write it as a sum of rank 1 matrices, how many matrices do I need? If I want to write a given matrix as a sum of rank 1 matrices, how many matrices would I need normally? Yeah, I should just need rank H, rank H matrices. But now what I want to do is I want to write it as a sum of rank 1 Hankel matrices. Right? That might be more difficult because, well, now I'm reinforcing that rank 1s, that the rank 1s also have this Hankel structure. So now write H as a sum of rank 1 Hankel matrices. So of course I'm always going to need at least rank H, but sometimes I might need more because not all of my rank 1s might be Hankel in my minimal decomposition that I get from usual matrices. Okay. Does that make sense? So in fact I claim that if I take the following matrix 0, 1, 1, 0, and then the rest is just 0, this is clearly Hankel. This is rank 2. But if I want to write it in this way, I'm going to need D rank 1 matrices, D rank 1 Hankels. We will actually see later in the talk why this is true. And we will also see later in the talk why these two problems are equivalent. But I wanted to give you this one. Well, it's completely equivalent to that one. Also, I don't know, I think there's probably a lot more papers written about Hankel matrices than about bivariate symmetric tensor decomposition or bivariate Waring problem. But over R, so basically, okay, so what this question we can ask, so I specifically put k, x, y, but k can be R or C, I mean for us. These are the two fields of interest for this talk. And over C, everything about this problem, or equivalently this problem, was already understood very well by Sylvester. So it dates to 1850s, maybe 60s, something like that. But over real numbers, there are still quite a few things that are not very well understood. Okay. So, are there questions? Are we okay? Do we understand what I'm going to spend? You know, you're going to spend like the next 55 minutes in this talk. Do you understand what I'm going to talk about? Is this okay? Yes. Okay. So let's move on. So the main, what is the main tool here? And this is also basically, well, in bivariate case is also due to Sylvester, but maybe not in non-bivariate case more recent. So it's called apolarity lemma. So I need to introduce a few things. So here the discussion is going to be general. For a while it's not really bivariate. So, okay, so I need to define a polar ideal. Okay, so now given a polynomial G, doesn't matter in how many variables. If I write G as the sum of C alpha x to the alpha, this is multinomial notation, I can associate to it a differential operator, which just does exactly what G does, except with differentiation. So basically, if I see x1 squared, then I replace it with differentiating by x1 twice. And okay, so now I define a polar ideal of F as the set of all G's such that differential operator of G kills F. Okay, so maybe an example. So if I look at x, y to the d minus 1, it's easier when I pick a monomial, right? You could think, you know, what differential operators are going to kill this? Well, so certainly x squared, when I took a differential operator of x squared, that's going to kill this guy because I differentiate with respect to x twice. The differential operator of y to the d is going to kill this guy. I'm differentiating with respect to y too many times. And in fact, I guess I should write perp. So the apolar ideal is generated exactly by these two guys. X squared y to the d. And in two variables, these apolar ideals are very well understood. So fact, maybe, I'm not sure who this is due to. Maybe, probably it's already known by Sylvester, but fact exercise. So when F is bivariate, so this is very special to bivariate, I will say a few things of what happens for more variables, but anyway, so when F is bivariate, then F perp is always generated, it's always like this, so it's generated by two guys. And maybe this is too low. Is it too low? It's okay. So, well, okay, yeah, but then I'm also going to move even lower, so let's avoid that at least. So F perp is always generated by two guys. And in fact, we know even quite a bit more. We know the degree, well, kind of know the degrees. We know the sum of their degrees. The degree of G1 plus degree of G2 is D plus 2. And G1 and G2, let me say it in words, have no zeros, no common zeros over C. or in more advanced, slightly more advanced language, they are a complete intersection. Okay, so this is what's known about bivariate apolar ideal. So if you take more variables, then in 3 variables there is the Buchsbaum-Eisenbach structure theorem that essentially describes all apolar ideals in 3 variables. So it's beautiful but a bit more complicated. And if you go to 4 or more variables, then I think it's fair to say that it's very much wide open. Despite there being many sort of partial results, there is nothing that comes close to touching any sort of classification, even for small examples. So even if you fix, I don't know, your degree to be not too large, so you don't ask for anything in 4 variables, but I don't know, but you fix some not too small and not too large degree, we still don't really know what's going on. Okay, but luckily for us, today we're talking about bivariate things. So here we understand everything. So, okay, so now what use is this apolar ideal? Well, the use of the apolar ideal comes from apolarity lemma. So I'm going to state it for bivariate forms, and it's going to be an exercise to generalize the statement and maybe even prove it for a higher number of variables. Okay. So apolarity lemma. So we have f is a bivariate polynomial. And now I can write f as a linear combination of sums of powers. So now every Li I can write, it's a linear form, aix plus biy. So f can be written in this way if and only if the following polynomial, so I form a polynomial g, which is b1x minus a1y, b2x minus a2y, up to however many, brx minus ary. So this guy, so G is in the apolar ideal of F. So the differential operator of G kills F. Okay. So what's going on here? Especially you look at this, why are A's and the B's switched? Why is there a minus instead of plus? What is the meaning of this polynomial? Right? What is the meaning of this polynomial so that we can generalize it to higher number of variables? So the idea is the following. So notice that, okay, so these LIs, I can think of them as being dual to points AI, BI in P1. If you want, I should really make them projective. And how is this polynomial built? This polynomial is a polynomial that vanishes at all of these points. And in fact, this is special for bivariate. It is the generator of the principal ideal of everything that vanishes at these points. Okay, so in fact, this G just generates the ideal of all bivariate polynomials that vanish at the points corresponding to the decomposition. Okay, so hopefully this can point you toward the correct generalization in more than 2 variables. Questions? Okay, so now let me sort of say this again. Well, not say it again, but what is apolarity lemma? Let me sort of say it in words. What is the bottom line? What is apolarity lemma saying about the rank of F? It is saying the following. So the apolarity lemma says that this is kind of a better, well, I prefer to think of it this way. So it says the following. Rank F or this is an implication, is equal to R if and only if a polar ideal of F contains a form G of degree R such that G has distinct roots and factors completely. Well, if it has distinct roots, it's going to always factor completely over C, but factors completely over K. So in particular, the particular relevance for us is K equal to R. Okay, so this is and also you need this, that this doesn't happen. This doesn't happen in lower degree. So basically what the apolarity lemma says is the following. Look in the apolar ideal, find the smallest degree in which your apolar ideal contains a function with roots in all of the roots in the field you want and roots distinct. That's your rank. So now we can see a difference between R and C. So notice that, by the way, so let's do an example. What does a polarity lemma say about the rank of x, y to the d minus 1? So the apolar ideal, the apolar ideal is generated by this. So what is going to be the rank? If I look in the apolar ideal, in what degree can I see something with all distinct roots?
X, y to the d minus 1 minus x to the d minus 1?
Right, so I have to go all the way up to degree d. That's the bottom line, right? Once I hit degree d, I have two polynomials with, I can generate two polynomials with no common roots. I can make the roots distinct. But up to degree d, I cannot do anything. Right, this is clear. So then rank F.
I think you have y to the d.
Oh, sorry, y to the d. Sorry, yeah, that's right. Rank F x, y to the d minus 1 is equal to d. Sorry, yeah, that's right, because y to the d is in the apolar ideal, not y to the d minus 1. Y to the d minus 1, you can see, does not kill it if I apply the differential operator. Also, you can see, this is actually easy to prove, that over R or over C, it follows from this that rank F, it follows from apolarity lemma plus the knowledge of apolar ideals. It follows that rank F is at most D. And in fact, you can see that rank F equal to D is possible. You can also see that, over C, if you want to achieve rank D, this is basically the only way you can do it. Because you need to have because essentially you need to make sure that both of your generators can only come into play when you have rank D, when you have degree D, right? And in order for this, because the degrees of generators add up to D plus 2, one of the generators must be quadratic, the other one must have degree D, and the quadratic generator, if it has distinct roots, then the rank is 2. But if it has double roots, which means that it's exactly a square, then the rank is going to be D. Are there questions? Okay, so I guess let me add one more comment. I should have actually said it when I stated this fact/exercise. There is also sort of the other, you can also have an implication the other way. So if you give me G1 and G2 that have no common zeros over C, degree plus G of G1 is equal plus degree of G2 is equal to D plus 2, then if I look at the ideal, it is going to be the apolar ideal of some F. So you can also go the other way. So basically, in a way, there is a sort of a perfect correspondence between between pairs of polynomials like this and and forms of degree D. So, okay, so now let's do another example just to illustrate the difference over C or over R. So imagine that I have a polar ideal is like this. In a way, I don't really need to bother computing what this is apolar to. I know that these two things have no common zeros. I know that their degrees add up to the same thing, so they are going to be apolar or something of degree d. You can figure out what it is. Let's say that's an exercise. But what do I know about the rank of this thing, or the real rank of this thing? What is the difference between real and complex rank here? So what is the complex? Let's go first. What is the complex rank of this guy? 2, right? Because this is a guy with two distinct complex roots. But over reals, what is going to be the rank? How far do I need to go before I can find something that factors completely over reals? Right, I have to go all the way up to D. So the real rank, so rank R is D, and rank C is 2. Okay. So maybe a little bit, okay, so this apolar ideal seems awfully useful. How does one compute it? So,
sorry, that's the apolar ideal of what polynomial I missed?
That's an exercise. I'm claiming that it is apolar to something because I know that these two guys are a complete intersection. So it's an exercise to figure out what this polynomial is. Okay, so yeah, so this apolar ideal seems awfully useful. So how does one compute it? So again, this goes back to Sylvester. Even so far, there's the name was made up by him. Maybe not the most well, nice choice, but I think according to Bruce Resnick, the original name was even longer. So catalecticant is the shortened version of the name. So, okay. So, all right. So let me take a bivariate form, and now I'm going to write it with a slightly rescaled coefficients. Di choose I x. Okay. So actually, let me before I write anything down, what is a polar ideal doing? So what does it mean? So let's ponder the meaning.
Yeah, it's D choose I probably.
Oh, yeah, D choose I, sorry. Yes. What is the meaning of dg of f equal to 0? What is it saying? Well, it's saying that somehow there is a linear relation between partial derivatives of f of some order. Right, so for example, if degree of g is equal to r, saying that dg of f is equal to 0, it is essentially saying that there is a partial, there is a linear relation between rth partial derivatives. Okay, so now if I write f in this form, I can form the kth catalectic, or I think mth catalecticant matrix Cm as follows. So now this is something where I'm going to get the subscript wrong. So let me look at my notes and hope that that has the subscript right. So you start with, so you take these coefficients and you arrange it in a matrix that sort of has Hankel format, but is not necessarily square. And you go all the way out to CD minus M, Cm, C0. So I claim, so now this is the so-called mth catalecticant. And in fact, well, once I tell you how to interpret this matrix, you can generalize it to more variables. So, okay, so how to interpret this matrix? I claim that actually every row every row of this matrix corresponds to a, I guess, mth partial of f. Mth partial derivative of f. So for example, the top row corresponds to d dx to the m. And then the next one corresponds to d dx to the m minus 1y. I'm hoping that these numbers correspond very well with the subscripts, but I might be making a mistake here. But anyway, every row corresponds to an mth partial of f. So basically, if I compute the kernel of this, this is going to give me all linear relations between the partials. Or this is going to give me exactly the kernel. So the kernel gives me all linear relations. All linear relations are exactly what's in the apolar ideal. So exercise. Kernel of Cm is equal to the degree m part of f perp. So basically, I guess bottom line is what I'm saying. How do you compute a polar ideal? It's linear algebra. All right, so what do? You take the coefficients, you rescale them, you put them in the matrix, you compute the kernel of the matrix, you reinterpret it as a polynomial, you have your degree m part of the apolar ideal. And I mean, the same setup in a slightly more advanced way generalizes to more variables. So you can think about that as well. Okay. Are there questions? Okay. So now, right, where did my Hankel matrix come from? So that I gave you this original example in the very beginning of the talk, and I said that decomposing F corresponds to decompose, it's equivalent problem to decompose some Hankel matrix in terms of rank 1 Hankel. So when the degree D is even, you can take the middle catalecticant. Okay, so when D is 2k, you can take ck. It's going to be now a square k plus 1 by k plus 1 matrix. It's going to exactly have the Hankel format, C0, CD, CD minus 1, CD minus 1, all the way down to C0. So I'm going to call it HF, the Hankel matrix of F. And another sort of exercise. So what does this correspondence do? So basically, I can equivalently think between the polynomial or the Hankel matrix. I see all of the coefficients of the polynomial in the Hankel matrix, so you could think of there is, I don't know, a linear map, or there's just a one-to-one correspondence between polynomials and Hankel matrices. But then you could ask, what do rank 1 Hankel matrices correspond to under this correspondence? And the exercise is rank H. So rank HF is equal to 1 if and only if F is some dth power of a linear form. So that's where the equivalence between the two problems come from. I can think about the polynomial of even degree or its corresponding Hankel matrix. And then if I decompose it as a combination of powers, this exactly corresponds to decomposing this matrix as a linear combination of rank 1 Hankels. That's all that there is. Okay, so in a way, this is just really general background on Waring problem in two variables. So I will now go into sort of more what happens over reals, and maybe after making one more point. Are there any questions right now? Okay, so now what happens? What happens to this problem over C and over R? Why is there a big difference? Well, one difference is the following. So, okay, so F perp is generated by G1 and G2. This is always true. You know, linear algebra works the same way over reals or over C. Right? Nothing really changes. So you can compute F perp just using linear algebra. And the degree of G1 plus degree of G2 is equal to 2. Oh, sorry, is equal to D plus 2. So now, basically what happens is once you start computing these catalectic matrices with generic entries, or in other words, for a generic choice of polynomial f, you expect these guys to have full rank for as long as they have, for as long as it's possible, for as long as they're, well, you expect them to have full rank always, but you expect them to have no kernel for as long as it's possible. And for as long as it's possible means as long as there are more, which one is it? As long as there are more rows than columns, you expect there to be no kernel. Okay, so you expect them to have no kernel for as long as you can, and essentially what it says is that outside of a Zariski closed set in Rxy, oh sorry, in Kxy. Always want to write it in reals. Outside of the Zariski closed set in Kxy, degree of G1, well, there are two cases. Degree of G1 is equal to degree of G2 is equal to K plus 1, where then D is equal to 2K when it's even, and the degree of G1 is equal to K plus 1, and the degree of G2 is equal to K plus 2 when D is 2K plus 1. So it's slightly different. There is a bit of a difference between even and odd degree. But in fact, yeah, so you might wonder what is this Zariski closed set. So Zariski closed set, so when D is 2K, this Zariski closed set is given by determinant of the Hankel matrix is equal to 0. So basically, as long as your Hankel matrix is non-singular, you have your apolar ideal, I will call generated in generic degrees. So your apolar ideal is generated in generic degrees. If your Hankel matrix is singular, then it's not generated in generic degrees. But in any case, this sort of occurs inside either over C or over R. It occurs on a Zariski closed set.
This is Zariski closed set in KXYD.
Oh, yeah, that's sorry. Yes, that's right. That's right. You can also write down explicitly what happens, when the degree is odd. But for this talk, I will mostly focus on the case of even degree, which is often, well, over reals is going to be more interesting, more delicate. So yeah, so what's going to happen? Okay, so what happens over C? Let me just finish saying it. So basically, let's look at even degree. When your Hankel matrix has full rank, you have two generators, both of degree K plus 1. They have no common roots. So this means that I can always find something of degree K plus 1 that factors completely over C. And this means that here, so basically, so degree is 2K if determinant HF is not equal to 0, then rank F is equal to K plus 1. It cannot be less than K plus 1 because there is nothing in a polar ideal of degree less than K plus 1. And similarly, if you are outside of a Zariski closed set, when D is 2K plus 1, then the rank is going to be again K plus 1. Because generically, your lowest degree generator is going to have distinct roots. Sometimes it will not, but generically it will have distinct roots. Okay, now over R, the situation is a bit different because basically there is no such thing as a unique generic rank. So here you see that outside of a Zariski closed set, the rank is exactly the same. And it's also pretty easy to figure out what it is. It's also, everything is known. So you can also figure out what happens, for example, when Hankel matrix is singular, how to determine rank. But over R, the situation is different. So over R, the situation is quite a bit different. So what happens over R? So let me denote by SR. This is the set of all forms of rank R. Okay, so now with definition, rank R is called typical if SR contains an open set in the usual an open subset in the usual Zariski topology of R, X, Y, D. And over reals, we know that essentially all of the eligible ranks are typical. So meaning that all ranks, so well, you can see that essentially you cannot have an open subset if your rank, so, yeah, well, let me first say this here. So all ranks are such that R is between the floor of D plus 2 over 2 and D are typical. So you can see by basically going through a polar ideal that if you pick too small, you have absolutely no chance of hitting an open subset. And we already discussed that the maximal rank can be at most D. So the key question is it true that everything in between is typical? And the answer is yes. This is actually more general. But initially this was conjecture of Camon and Ottaviani, who proved that this was typical and this was typical. And then they conjectured that everything in between is typical. And that's actually a more general phenomenon. Any rank between the minimal typical rank and the top typical rank is always typical, even if you don't look at bivariate things, even if you just look with respect to rank to a variety. But in any case, for us, we know that these are the typical ranks. And so I guess the main point of the talk is that very little is known about these sets SR. So let's just focus on the ones where we have a ball. Okay, so let's focus on the typical ones. So what can we say about these sets SR? So what is the set of all forms of a given typical rank? So we're within this range. Okay, so something very nice can be said for the top typical rank. So the top rank and top typical rank is D. So there is a very nice theorem to which I guess we made a tiny contribution. So the theorem is the following. So let me write some attributions, maybe in some reasonably chronological order. So what does it say? So it says rank F is equal to D if and only if F has only real roots. Such polynomial is sometimes called hyperbolic or real stable. So it says that F has maximal rank if and only if you have only real roots.
I don't understand. I mean, let's take F equal to X to the D.
Okay, if it's not a power. And F is not a linear, F is not equal to a power of linear form. That's the only exception.
But even if it has, so in the case that words higher multiplicity, that's not at all.
Yeah. So okay, let me state some. So I think let me state some what happened with this theorem. So I think Bruce Resnick proved this direction. And also conjectured that this is actually the case. Now, Camon and Ottaviani proved the whole thing when D was small, maybe, if I'm right, maybe something like 5. And they sort of laid out a plan of how one would prove it, modulo some work. if f has distinct roots. If f has distinct roots. And then this work was later done by Kausa and Ray. So this was a theorem, except that perhaps if f has multiple roots, but the multiple roots are complex, there was still no sort of, maybe it still has maximal rank. So essentially, our contribution is to remove the last little bit. But most of the work was already done by the people listed. So, but yes, so it works even if f has multiple roots. So you only if f has all real roots do you have that the rank is maximal, if and only if. Okay. So, but an interesting thing here is that even though we have, in a sense, sort of a perfect understanding of what's going on here, it's not clear. So basically, how does the proof work? The proof, I mean, all of these proofs, they work by induction. And in a way, it's very ad hoc. It's very ad hoc, so I could ask, can I understand this statement in terms of a polar ideal? Right, so f prop is generated by some p and q. How do I write out p and q so that I don't hit, and how do I know that I will not hit the form is all real roots, until very high degree? So this understanding is kind of missing. I mean, I know how to prove this, but the proof doesn't really tell me. So understanding this in terms of the apolar ideal is not very clear. Because the proof is inductive. The proof is inductive. It doesn't really tell you what's going on. Okay. So notice that, what else? I just want to mention a few things. So this set is basically almost closed. So what is set SD? So the set of all things of rank D, it is almost closed because, we don't have the powers. It's almost a closed set. Its boundary is essentially given by the discriminant. Well, its boundary is given by are polynomials with all real roots.
I don't understand what almost closed means.
Well, you have powers, right? So I can approach a power by something that has all real roots.
So it's only missing a small part of its boundary.
Yeah, I'm only missing a tiny part of the boundary in the set. If you don't like the almost closed, that's okay. You don't have to like it. I'm not forcing it to you, but from my point of view, if I take a tiny part of the boundary away, the set is almost closed. So polynomials with all real roots and multiple roots. And if you think about the algebraic boundary, meaning that I just take the de Reszke closure, then the algebraic boundary only has one component. It's given by the discriminant.
So are those missing points exactly the extreme points of that set?
Extreme? No, this is not. There's no convexity here. There's no convexity here. Okay. So now, basically, what I want to tell you is a little bit about what happens for the other extreme, which is the minimal typical rank. And I'm going to focus on the case of even degree, where the minimal typical rank is k plus 1.
Sorry, just
Yes.
the dimension of this set.
It's full dimensional, right? I can take a polynomial with all real roots. No matter how I perturb it, it's going to have real roots, as long as they're distinct. That's why it's typical rank. So it's full dimensional because I can perturb it and it will stay of that rank because of the characterization.
So if you use the usual measure of volume that people have been using, is this the largest or the smallest set of typical ranks?
Who knows? There is absolutely, there is absolutely no, okay, let me put it this way. So this case is well understood. I'm going to tell you something, a reasonable amount of things about this case, all right, the minimal one. And in between, I would say it's completely wide open to understand what these guys are. So before we start measuring their size, it would be reasonable, I'm just guessing. Perhaps you can measure their size without understanding things about them somehow, but...
Just It's either the largest or the smallest, right?
Why? I don't see. I guess my idea of justice does not correspond to.
Well, there is. I mean, in other sort of extreme settings, cases where you have sort of extreme amount of reality, that often happens on an extremely small set.
Right, well, okay. I really have not thought, what is the natural measure and so on. But I mean, in a way, this does not look small. I don't know. But maybe it is. Maybe I'm just not thinking about it in the right way. Okay. So, right. So what do I want to say about the minimal typical rank? So, yeah, let's focus on the even degree. So, yeah. So D is 2K. So I'm looking at SK plus 1. This is the guy this is the set of all forms with minimal typical rank. So I don't know, proposition. So SK plus 1 is an open set. It's not connected. It has, let's see, hopefully I will get this right. It's connected components. Maybe silly. And where do these connected components come from? So connected components, how I can enumerate them, they correspond to the signature, different signatures of the Hankel matrix. But of course I'm looking projectively, so signature means the signs of the eigenvalues. So if I'm looking projectively, f is the same as minus f, so plus 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 is the same as minus 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 minus. So up to this equivalence of plus signature and minus signature, they're exactly indexed by the signatures of the Hankel matrix. Yeah, these are the connected components. And I guess in order to understand this, so first of all, I guess exercise, or if the determinant HF is equal to 0, in other words, if the polar ideal is not generated in generic degrees, then rank F is not equal to K plus 1. So basically, if the Hankel matrix is singular, then I cannot have rank D plus 1. Why is that? Well, essentially, if the Hankel matrix is singular, I'm going to have a generator that has degree less than K plus 1. If it has all distinct real roots, then the rank is less than K plus 1. If it doesn't have all distinct real roots, then I will not be able to get all this, because you see the sum of the degrees of G1 and G2 is 2K plus 2. So if the degree of G1 is less than K plus 1, then the degree of G2 is greater than K plus 1. So either G1 has distinct real roots, in which case the rank is less, or if the G1 does not, then I have to wait for a while to hit G2 more than K plus 1, and that's the only way that I can get to distinct real roots, because obviously multiples of G1 are not going to suffice. Okay? So the bottom line is, so the singular guys are not interesting to me, and that means that, anytime I want to get from one signature to another, I have to cross, the eigenvalue has to hit 0, and that means that the signature, well, there should be at least as many connected components as there are signatures, and in fact, they're just indexed by signatures. So they're not more. And in a way, this also, you can draw sort of a mental picture. So this is it's a combination of a bunch of open sets. And I guess the mental picture is that these open sets, it sort of looks like a sausage. What do I mean by that? Well, if I start with the signature plus 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 plus, I can only, I cannot reach just any component, right? I can only change one eigenvalue at a time. So I can do plus 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 minus, unless I go through a specially singular point. Right, and then the next time I can only change, to another minus, and so on. So that's what I mean. It's kind of, in a way, laid out like a sausage. They're in a row. Okay. Questions?
Well, is this result possibly true also for odd degree?
Yeah, so there is a corresponding result for odd degree. Well, there is no signature of the Hankel matrix, but we can also describe the case of odd degree.
You have several cometric components.
Let me try to remember. I think the answer is yes, but maybe I'm misremembering something. I think the answer is yes.
Wow, that's really quite beautiful. Yeah.
So, okay. I guess, okay, so I want to say a few more things, but there is something that actually, there's something that's beautiful here that actually I still want to describe. So how can you, so there is a correspondence, in order to have degree d plus 1, in order to have rank k plus 1, you must be generated in generic degrees. So basically, what we're looking at, this one I actually want to keep. So let's go to this board. Okay. Let's go to this board.
Greg, can I ask you a question about this here?
Yeah.
In this proposition, suppose you replace every Hankel matrix by its inverse. Do you know whether that takes...
Well, but the inverse of a Hankel is not Hankel, right?
Of course. Do you know what happens to the connected components under that transformation?
I'm not sure. Because I'm not sure which space they lie. What space I should think of them. They certainly don't correspond to forms anymore, right? They just correspond to symmetric matrices. Okay. So off the top of my head, I don't have an interpretation of what's happening. All right. So how can you? So I have f, and f perp now. Let me just say is generated by p and q. They are of the same degree. The degree of p is equal to degree of q is equal to k plus 1. How can I read off the signature? Let's say I'm just given the pencil. So I'm just given pencil pq. I'm given two forms. So the pencil just refers to linear combinations, let's say alpha p plus beta q. How can I read off? Of course, if they have no common roots, it's apolar to something. So I can find the apolar thing. I can find given p and q, I can find the f. I can build the Hankel matrix. I can take the signature. But there should be a way for me to see the signature just by looking at p and q, maybe without computing all the way to the apolar guy, and then writing out the matrix and finding its signature. And in fact, the answer is yes. So how can I do it? So basically, what I want to describe is signature of HF just from P and Q. So here's how it works. I'm only going to say it in words, and then we can write down the theorem later. So let's say that the degree is 4, and so what is this? This is my picture of P1. RP1 is a circle. What I wrote down here are the roots of P and Q. Okay, so these are the roots of P and Q. I don't have a good term for this. I call it kind of an interlacing diagram. Okay, so these are the roots of P and Q, how they lie on P1. Now what I can do, I can make an equivalence relation. Anytime I have two roots of the same polynomial, I can make them come together without crossing the roots of the other guy, and I can make them disappear and make them complex. So under this transformation, this guy is equivalent to this. So, I can make these two guys go away, I can make these two guys go away, but now I cannot because they're completely interlaced. Right? So now there is no more reduction. So in fact, I claim that essentially the signature is in one-to-one correspondence to interlacing diagram, signature of HF, is in one-to-one correspondence to the interlacing diagram of a pencil. And for example, the fully interlacing diagram corresponds to exactly HF being positive definite, or in other words, signature plus, 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 plus. And then you can see, so as soon as you're taking, as soon as you start taking these guys away, if you have less interlacing, you're going to introduce negative eigenvalues. Okay, so now, so that's actually quite beautiful. Though I cannot say that I know how to prove it. I cannot say that I sort of fully understand it. Okay, and so now, right, so what did we say here? So this guy was almost closed. It's actually also, I forgot to mention, but this guy is obviously connected. So here we have, this guy is open. So the minimal typical rank, the set is open. It has several connected components. We can index them by either the signature of the Hankel matrix or the interlacing diagram. We know how to count them. So now what about the boundary of the set, or in fact, algebraic boundary? So let me state the theorem. So what is the algebraic boundary of this? So algebraic boundary of Sk plus 1 has 3 connected components. Well, one we already know. One is the determinant of the Hankel, or it's also called the middle, equal to 0. One component is just given by the vanishing of the Hankel matrix, or the middle catalecticant matrix. 2, so now let me remind, so F perp is given by this pencil PQ. So the pencil, just alpha B plus beta Q, so this pencil contains a polynomial with 2 double roots and 3 alpha p plus beta q contains a polynomial with 3 with triple root, I guess that's it, with a triple root.
Greg, do you mean just 3 components? Or do you mean connected?
Oh, sorry. Connected was not necessary. Yeah, I just meant components. Sorry. That was... guess because I was talking about connectivity, it's just kind of snuck in. Okay. So it has 3 components. I actually don't really know degrees of these guys, although I have a reasonable guess. So that's an open question. In fact, it's one of the exercises. Okay, so time is almost up. So what is it that I want to say? Well, let me maybe state one more theorem. So you could also ask, what about, so over complex numbers, let's focus on this case. So D is 2k, right? So D is 2k, and rank F is equal to k plus 1. So you could ask, what is the set of all decompositions? So F perp is, again, it's generated by these 2 guys, P and Q of the same degree. So then, in fact, when you look at the pencil, alpha P plus beta Q, almost any polynomial in this pencil is going to have distinct roots. And once you have polynomial with distinct root, it naturally indexes a decomposition. You just take the roots of your polynomial. This gives you the decomposition. I mean, you don't know the coefficients, but you know which linear powers to take, then you find out the coefficients. Okay, so basically over C, you can say that this sometimes called variety of sums of powers is naturally equal to P1. I mean, okay, at some points you hit a double root, but you take the risky closure, you have a P1 worth of decompositions. Now, what happens over R? Well, you look inside alpha p plus beta q, so again, you look inside RP1, so if you want a line, or I can sort of join it at infinity into a circle. And now what happens, well, you might leave you might leave. So at some point, because I'm not just interested in distinct roots, I want distinct real roots. So at some point, my pencil, which is just a straight line, it might leave a domain of hyperbolicity. So what I'm going to see is I'm going to see that, well, there's not really going to be a variety of sums of powers. I don't have a good name for it. It's a semi-algebraic set of sums of powers. It's going to be a bunch of open segments. So it's going to be some collection of open segments. And if inside here I have a polynomial with all real roots, it naturally indexes decomposition. But at some point, if I take different coefficient, so this is alpha p plus beta q, alpha 1 plus beta 1. But at some point, if I take a wrong coefficient, I might leave the domain of polynomials with all real roots. So then you could ask, what is the largest number of open segments that I can have? Right, so how many times can I take a pencil and make it enter and leave the domain of hyperbolicity? And the answer is sort of maximal possible. So maximal possible. So let me state the theorem. So theorem says, so it's possible that alpha p plus beta q so VSOP, how should I put it? The variety of sums of powers of F, where F perp is PQ, can have at most K plus 1 open segments. And any number between 0 and K plus 1 is possible. Now let me just say, why is it K plus 1? Because, so what's happening here? What is really happening here? So I have a pencil of polynomials. Now I can think of this pencil as just a straight line. So I have alpha p plus beta q. So projectively, this is a line in R, X, Y, K plus 1. Okay, so what I have is a line. And now anytime I enter, so this is the discriminant locus. Discriminant locus. Anytime I enter the domain of hyperbolicity, I must cross the discriminant locus. Anytime I leave domain of hyperbolicity, I must cross the discriminant locus. So every open segment corresponds to taking crossing the discriminant locus twice. Now the degree of the discriminant locus is 2 times K plus 1, because I have forms of degree K plus 1. So this means that, if every time for every segment I pay a price of 2, I can have at most K plus 1 segments. The only question is whether actually I can contrive every time I cross discriminant locus to essentially enter, leave, enter, leave, enter, leave, enter, leave. And what I'm saying is the answer is yes. Okay. I am out of time. Actually, I'm over time, but I've said all that I wanted to say, so I apologize for extra time, and thank you.
Are there any questions? Yeah.
This number, this signature is also the degree of the real algebraic mapping from the circle to the circle. Right? And I wonder if that can be useful in this, or if you do use that.
Wait, so which number? So you're talking about the signature of the number of different signatures of the Hankel matrix?
I believe the symmetric form defined by the Hankel matrix is the form on the middle degree.
That's right.
Of the algebra.
That's right.
And that's also the topological degree of the map defined by P and Q.
Oh, that's that's right. In a way, do we actually ever use that?
That's what these interlacing diagrams are sort of doing.
Right.
Because zero changes.
Yeah. I mean, in a way, we do use it, but maybe indirectly. I mean, yeah.
So the other thing I wanted to ask is whether you know anything about the set of Fs in more variables which give complete intersections.
Oh, the set of F such that the apolar ideal is complete intersection. No, I don't know too. I mean, the only thing that I can say is that when you have a complete intersection, it's usually pretty easy to determine what the Waring rank is. I mean, so that's very helpful, but I don't know. Yeah, I don't know how to parameterize these things in any sort of reasonable way.
So about those numbers. So 0, if you had these totally interlaced,
Uh-huh.
the roots of P and Q totally interlaced, you would get 0, right? You would always have real roots. And
That's right. Your entire line would stay inside the domain of hyperbolicity.
Is K plus 1 when they're sort of totally uninterlaced?
That's certainly one possibility. I mean, because I.
Have you looked at the pictures for each of them?
That's right. So I mean, yeah. So you can make some statements. So for example, if they're fully interlacing, then for sure your thing is your line is going to stay fully within the domain of hyperbolicity. I don't remember. So certainly, I mean, because essentially I just have a construction. I just have a construction that does it k plus 1 times. I don't really have a full understanding, and I haven't thought about this enough of what are the sets of all things where you cross k plus 1 times. Do they all come from just one connected component of the set, meaning from one set of interlacing diagrams? I'm not completely sure. In fact, there are a lot. So I guess one thing that I wanted to say is that there is a ton of open questions here. So I mean, this is just the minimal typical rank, and we understand the maximal typical rank. Everything in between is actually much more complex. Well, I don't know really how to do things because, I mean, essentially there are two ways that I know how to do things. One, for the top rank, we have an ad hoc way. Sorry, it was on this board, but no longer. We have the ad hoc way of inductive proof. For the minimal guy, the apolar ideal works well. But now how do I describe such pencils P and Q so that alpha P plus beta Q doesn't contain something with all real roots, but when I multiply by linears, they do? This becomes much more complicated. I don't know of a good way of thinking about it. In fact, if I start thinking, so this is kind of strange, but if I don't think about the result for maximal rank in an ad hoc way, but I try to think about it in the apolar way, it becomes very unclear. How do I define these two guys P and Q so that no combination of them will have a form with all real roots until I'm forced to have it? So in fact, maybe if I understand this, then this will be the key to understanding everything in between, as opposed to the inductive way of doing things. But in any case, there are actually a lot of open questions here, which I think is a little bit surprising. I mean, we're talking about polynomials in one variable or Hankel matrices, but anyway.
What's your conjecture about the maximal typical rank for more variables?
No, but there is no general conjecture. There is not even conjecture for the maximal rank. Well, I don't know. In fact, I don't know which one is more difficult, the maximal rank or the maximal typical rank. But something that me, Giorgio, and Alessandro have been stuck on for a while, which is the smallest open case is ternary quartic. So you could ask, what is the maximal typical rank defined in exactly the same way of ternary quartic? Or just the maximal rank of ternary quartic, both are open. So I did put it on the exercises, but I wrote in the parentheses maybe harder. I'm not sure, in fact, because in a way, I think that we need some new ideas. And with a new idea, this might actually be for ternary quartic and not in general. For ternary quartic, this might actually be a not very hard question. But without new ideas, it seems reasonably difficult.
Another question? So let's thank Greg again.